All right, we're back. We are still on page 9 of notes analysis. Of what? I don't know what I even said. I think I might have said notes analysis. I don't know. We're on page 9 of notes 1 of math analysis. And now we're going to talk about complementary and supplementary angles. So there's going to be a weird little twist to this that maybe you didn't encounter in geometry. And the twist that you are going to encounter is that sometimes an angle will have a negative complement or supplement, and we're okay with that because what we're interested in is the sum of the two things. We don't so much care what the two things are. We're going to find out later in the course that things that add up to 90 or add up to pi over 2, they have certain properties, right? And it actually won't matter if it's two positive things, so like 10 degrees and 80 degrees add up to 90 degrees. They're definitely complements. 100 degrees and negative 10 degrees also add up to 90. They are complements for our purposes. So this is a weird new thing, maybe. Maybe it bothers you, maybe it doesn't bother you. But in general, you do have to remember what complementary and supplementary mean. But I always learned it's right to compliment people, like that complimenting people is the right thing to do. Forms a right angle, 90 degrees. That's how I learned it. And then we also have supplementary, which I did not learn anything about because if you remember what complementary is, supplementary is the other one. So if we're in radians, we have to use pi over 2 and pi. If we're in degrees, we use 90 and 180. Not a big deal, but you got to keep track of it. All right, so in degrees, if I want to find the complement, so in degrees, I'm going to be doing like 90 minus x, I guess. 90 minus x. If I am in radians, I'm going to do pi over 2 minus x. So for the first one, I'm going to say it's 58 degrees, because if I subtract 32 from 90, I get 58. If I subtract 142 from 90, I get what? I think I get negative 52 degrees, and that's okay. We're allowed to have a negative complement, which is it's bothersome, right? It's a little annoying to have a negative complement, especially because you probably at some point in your life lost points for putting a negative complement. But like, it's a thing. We're allowed to have it. All right, let's do the supplements while we're here, right? So it's going to be 180 degrees minus x, or it's going to be pi minus x. Just depends on what we're using. So for the first one, if I subtract 30, I get 150. So this will be 148. And then if I subtract 142, I just get 38, which in my mind, I always check by like adding back in. So both of these have positive supplements, but like 200 degrees has a negative supplement because you have to add negative 20 to it to get to 180. So supplements could be negative. They don't need to be positive for our purposes. Next row, the next two columns are in radians, so we're going to use the other formulas. So here's the thing, right? So you want to develop sort of a number sense for radians, and it's not that easy to do, but it's not that bad, right? So pi over 2 is half of pi. So if I want to write pi over 2 with 7 as the denominator, I just need half of 7 in the numerator. So like I would need 3.5. So if I were going to show work for this, which I kind of think is a weird thing to do, but I might do 3.5 pi over 7 minus 3 pi over 7 is 0.5 pi over 7, but I would not leave that. So this is how I would solve the problem. And then I would turn 0.5 into 1/2. Pi over 2 divided by 7 is pi over 14. So that's how I would actually do it. Finding the supplement is going to be super easy because all I need to do is pi minus 3 pi over 7. So pi is 7 pi over 7. So 4 pi over 7. It's actually, in a lot of ways, it's easier to find supplements and complements when you're using radians. Depends on how you feel about fractions. I prefer fractions to decimals. I think all the calculations are a lot easier because you don't have to deal with all these decimals involved. But it's up to you. So here, what am I thinking? I want to do pi over 2 minus 6 pi over 11. Pi over 2, I'm going to think of as 5.5 pi over 11. So 5.5 pi over 11. Then I'm going to subtract 6 pi over 11. That gives me negative 0.5 pi over 11. Negative 0.5 is negative 1/2. Negative pi over 2 divided by 11 is negative pi over 22. That should be the complement. It's negative, not a problem. We can have negatives. Here we just need to do 11 pi over 11 minus 6 pi over 11 to give us 5 pi over 11. Straightforward. Now these two columns, do you see a degree sign? I see no degree signs. These are naked radians. There's no pi because they're naked, but they're radians because there's no degree sign. These are naked radians. Converting these is just weird. So what am I going to do? I'm going to do pi over 2 minus 1.2 and just live with it. That's as good as it's going to get. You could get a decimal, but the decimal, because of pi being irrational, the decimal you get is at best an estimate. Like you can at most round that. You could never get an exact decimal. So why not use the exact answer? So here we'll just get pi minus 1.2. So pi is 3.14, so pi over 2 is like 1.57. So that they're both positive, which is good. Well, which is, I'm saying good, like who cares? So here I'm gonna have pi over 2 minus 2.7, definitely negative. So this is negative, but it doesn't matter. It's allowed to be negative. And then here we'll just have pi minus 2.7. So you do want to think about pi occasionally as 3.14. Like keep that in the back of your head. Like the pi that we talk about in radians is 3.14 blah, blah, blah radians. That's exactly what it is. Well, exactly. That's the approximation of what it is. It's the decimal equivalent. So let's see what this next problem is. It's kind of like out of left field, but it's kind of like how do you think, right? A lot of this class will just be about like learning how to think better, how to think more deeply about things, how to think in a more flexible way. Like you want a lot of approaches because you never know when one's going to work and when one is not going to work. All right, so problem, a wheel moves with constant speed that makes it, so for reasons that are physics-based and vector-based later in your life, a wheel can't move with a constant velocity or it can't spin with a constant velocity because like things are always like change. It's fine though. A wheel moves with constant speed, makes a complete revolution every 20 seconds. All right, I can imagine that. At t equals 3 seconds, a point on the wheel is at the exact top. So I'm gonna start drawing because when you're reading a problem and it's giving you like things, okay, that didn't work at all. I mean, it worked to do something, but not the circle that I was hoping for. There we go. Okay, so we got our wheel, potentially. And then we're gonna have here, let's say that this is at t equals 3. Okay, makes a revolution every 20 seconds. 3 seconds, right functions that give these, okay, so which way does this thing spin? We don't actually know which way it spins. All the time, if you don't know which way something spins, assume that it spins counterclockwise. It's gonna make your life so much easier. So I'm gonna say we go this way. All right, if it takes us 20 seconds to make a full revolution, how long does it take to make each quarter revolution? This is a process that you're gonna go through a lot. So it's 5 seconds per quarter revolution, which means we'll get here at t equals 3 plus 5, or 8. We'll get here at t equals 8 plus 5, or 13, or t equals 3, and then add 10 because you went half of the circle. Then you get here at t equals 18, just add 5. Then you get back to the top at t equals 23. So maybe I'll also say comma t equals 23. Then you're going to keep going forever. The interesting thing is we actually want to write functions for when you get to each of these points, right? So we have a left point, a bottom point, a right point, and then I'm going to say an upper point so that I don't have to use t twice. So we want to write functions that give the exact times at which the point will be at the top. All right, so we're calling the top the upper. So I'm going to say upper of t. All right, so we know that at t equals 3, we're there. So 3 plus, well, if it takes 20 seconds to go all the way around, every time we add 20 to 3, we'll get to the top again. So let's say 20t. And then we need t to be an element of the integers. All right, so that does it. That'll put us at the upper point, the leftmost point. So I'm gonna use capital L of t. All right, the first time I get there is 8, and then I'm just gonna keep repeating this. T is an element of, So could you use t as an element of the integers once? You could, but that's lazy, and we're trying really hard to not be lazy. Bottom point. So you get there at 13, and then every 20, you're gonna repeat. So this is not bad, but it's like the kind of thinking and reasoning that you need. It'd be way harder to figure out other points on this. Later in the year, we're gonna definitely figure those out though. The rightmost point is gonna be at 18 the first time, 20t, t is an element of the integers. Okay, so I would say that these are, I guess we could kind of like try to color code, right? Here is when you're here, and then here for this, and then you gotta use different colors if you're color coding here. Why did I? This point is the bottom, and then this point is the rightmost point. So there you go. Those are our formulas that'll put us in these places. So now we can figure it out, right? So if you want to know, I don't know, if t is equal to 10, so at 218, you are definitely at the rightmost point. When t is equal to 218, rightmost point. And you can use these, and that's kind of useful. Write another function that generates each of the times but doesn't distinguish. Okay, so that's just like telling you what time does a train pull into a station, not necessarily the upper station, left, bottom, or right, just a station. Like, can I get on a train? So, I mean, how far apart are each of them? They're all 5 somethings apart, 5 seconds apart. So if I start, so let's call it S for station, I guess. I have decided these are stations. At t equals 3, you're definitely at 1. And then every multiple of 5, add every multiple of 5, rather, you're going to get to another one. So 8, then 13, then 18, then 23, and so on and so forth. So this also, t, is an element of the integers. So much harder to write on an iPad, that element of the integers thing, but you know, you got it. So we did some stuff here. Complements and supplements, not new ideas, maybe new in Radians, I guess, but they can be positive, they can be negative. That's a big difference. And well, maybe it's a big difference. Depends on the geometry class that you took, actually. So we did that, and then we looked at this. We just came up with some generalizations about something that's kind of moving in a circle. Moving in a circle is a very trig thing, although it doesn't feel it when you first start doing it. So I'm going to stop this here, come back in the next video, do some more stuff. Hope to see you there. I hope you're finding these helpful.